Hello people, this video is an intro to kinematics, and it discusses why the formulas and the graphs that you see in this unit kind of come together and make sense. So let's first look at the graphs. This is a distance versus time graph, or displacement versus time graph, and it's a diagonal line going up, so equal slope all the way. This is a velocity versus time graph, which is a straight horizontal line. Again, these represent constant velocity. Why? Because velocity is just the rate of change of displacement, or the slope of displacement, which is, as you know, change in y over change in x. The displacement versus time graph has x on the y-axis, though, which is kind of confusing, so we'll just change that to d. So change in d over change in t, which is on the x-axis. T is on the x-axis. As you see, I kind of labeled them. Just a little side note, the velocity versus time graph is a horizontal line because it's a graph of the velocity, and the velocity, again, is constant, so it would make sense for the value of the velocity to stay the same. But back to the displacement versus time graph, we need to find the equation of it. And as you know, the equation of a line in point-slope form is y1 minus y equals m times x1 minus x. Another way to say that is change in y equals m change in x. But on this graph, the y is d and the x is t, so it would be change in d equals m change in t. Why does this work? Because m is really change in d over change in t, and as you see, the two t's cancel, and you get change in d equals change in d. Now, to find the equation of the displacement versus time graph, you just substitute velocity in for m, because velocity, again, is the slope. So, change in d equals v times change in t, as opposed to m times change in t. We just substituted in the v for the m. Now take a look at the velocity graph. This is very cool. So it's a rectangle, right? V is constant, and t is the base. So if you look at the rectangle, right, the area of a rectangle is b times h. And in this case, the base is t, and the height is v, so a equals v times t, which is the same as the equation of the displacement versus time graph, which means the area of this graph is really what the displacement versus time graph is graphing. And so the area of this graph, of the velocity versus time graph, is displacement. That's kind of cool. Let me emphasize that because this is going to come up later in the video. The area of a velocity versus time graph is the displacement. Okay, but what about changing velocity? How would you calculate things? How do you graph that? So we're going to say there's constant acceleration. So you're going to need three graphs, one of displacement, one of velocity, and one of acceleration. The displacement versus time graph with constant acceleration looks like a parabola. The velocity versus time, a diagonal line, and the acceleration versus time, a horizontal line. Now acceleration is just the slope of velocity, so change in v, change in y, over change in t, change in x. And here, the slope is constant, so it creates a line. Constant slope creates a constant line, obviously. And as we said before, the formula for a line is the slope, change v over change in t, times t equals change in v, because the two t's cancel, right? So change in v equals at, because a is change in v over change in t. But how do you find the area of this graph? Well, you can't just do v times t because v is not constant. So you could approximate it by creating these small rectangles, right? And so they're kind of stacked up against each other, and it's like an approximation of the area. It's not going to be exact. And as you make smaller and smaller rectangles, you see that this graph is getting closer and closer to just a triangle. So how about we find the area of this triangle to find the displacement? Because the area, let me emphasize this, of velocity versus time graph is the displacement. So the area of the triangle is half times bh. B is t. H is the final velocity, vf, right? And now in this case, vf is at, because acceleration times time, again, is velocity. So you get half times at times t. That's a bit cut off, sorry, at the bottom. Or half times at squared. Now, as you see, I labeled the displacement versus time graph d equals half at squared, because displacement is the area of the velocity versus time graph. Okay, but here's something cool for you calculus people. So the derivative of parabola x squared is 2x, or the exponent times the coefficient times x, right? But what about the derivative of half at squared? Well, that would be the exponent 2 times the coefficient half a times t, or just at because 2 and 1/2 cancel. And at is just velocity, so you see the displacement derivative is velocity. Okay, so now for my favorite part, equations. Initial velocity plus at equals final velocity, or v0 plus at equals vf. Now here's a velocity versus time graph. V0 is the initial velocity and vf is the final velocity. The slope is change in v over change in t, or acceleration. Here's the equation of a line. Change in v equals a change in t, as we've said before. Sorry, the bottom's a little cut off. It's really not important. What you need to know is that change in v equals at. So, v0 plus change in v would make sense, as you see from the graph, for that to equal vf, right? All this equation is doing is substituting in at for change in v, as we've established here that at equals change in v. So that's why that equation actually works. But why does change in v equal at intuitively? Well, every increment of time you're adding a. So you're adding a total of t times, or a plus a plus a plus a, which is just a times t. Here's another formula which may be more mysterious in its origins. Distance, x, equals v0, initial velocity, times t, plus half times acceleration times t squared. Now, at is change in v, as we've already established, because a is the slope, change in v over change in t, times t, the t's cancel and you get change in v. And so half at equals half times the change in velocity. And if you add half of the change in velocity to v0, as I show on this graph here, then you really get the average velocity. But let's go back to the equation. So x equals t times v0 plus half at. If that's just factoring out the t. And so v0 plus half at, as we said from the graph on the bottom, is just average velocity. And average velocity is the total displacement over the total time. And so when you multiply the average velocity by t, then you just get change in d, or x. So let's look at this graphically. Again, I'm drawing the same graph, velocity versus time graph, with the velocity starting at v0 and ending at vf. So, if you find the area of this figure, which again is the displacement, you see that it's really two figures, a rectangle and a triangle. So the area of the rectangle is base times height. The base is t, and the height is v0. So that's the first part. The area of the triangle is half bh, half times base times height, or half times the change in velocity times t, right? Sorry, I added an extra t there. So half times the change in velocity times t. Now, you could substitute at in for change in velocity, as we said before, so you get half at squared as the area of the triangle. You add those two areas together, you get v0t, the area of the rectangle, plus half at squared, the area of the triangle. One interesting thing to note is that the area of this triangle is really half the area of this total top rectangle that I'm drawing here, because that's expressed in the area of the triangle, which is half BH. And the algebraic proof that I showed you before showed the average velocity being halfway in between the initial velocity and the final velocity. So no matter how you split the top triangle, whether it's the average velocity or whether it's as a triangle, you're still getting half of that rectangle, which is why these two proofs really work together to prove the same thing. Now another formula that you might see is vf squared minus v0 squared over 2a equals x. Another way you might have seen this is vf squared equals v0 squared plus 2ax, but I much prefer the first version because I think it's just more intuitive. So, we've seen this before. A equals change in v, sorry that's cut off, that's a v, change in v over t. or change in t, sorry. A equals change in v over change in t. Now, if you multiply both sides by change in t, then you get a change in t equals change in v, and divide both sides by a, you get change in t equals change in v over a, which is useful if you don't have t and you have change in v and acceleration. Now, I'm going to I'm going to substitute vf minus v0 in for change in v because that's really the same thing. Another formula that you may know, or that I've showed you before actually, is average velocity times t equals x. And I'm going to substitute in our new formula for time in for t if we don't have t. So vf minus v0 over a. That's the same as t, so average velocity times time, but it's just a little more complicated than that. Now, another way of saying average velocity is the average of the initial velocity and the final velocity. So v0 plus vf over 2. So that's the average velocity. Now I'm writing in the new formula for time. So vf minus v0 over a. So average velocity times time, or those two more complicated versions, equals x. And I now multiply that out as dots. So vf squared minus v0 squared over 2a, because you multiply the denominators of the fractions. And that's the original formula. Now, one thing that's kind of cool is that we already found the area of this graph that I'm drawing by adding the area of the rectangle on the bottom by the area of and plus the area of the triangle on the top. But now let's look at it as a sideways trapezoid, which is what this formula actually does. So, the area of a trapezoid is b1 plus b2 over 2 times h. Now the b1 is b0, b2 is bf, divided by 2 times h, which is t. Now, the reason why h is t is because this is a sideways trapezoid. And so d really equals v0 plus vf over 2 times vf minus v0 over a, which is what we said was time before. And now you multiply that out, and you get the original formula, which again is really cool. Now, that's all the formulas for today. Hope you enjoyed, and I'll see you soon.